one important concept in theoretical statistics, out of many, is unbiasedness of an estimator. So we have two estimators, beta 1 hat and beta 0 hat. We want to find the unbiasedness. Well, what is bias? In simple terms, you tell me. What does bias mean to you? So when you have a biased estimator, the value that you estimate is going to be in too much favor towards the data or way far away from the data. Agreed? So in other words, you have the data and you're coming up with a model that's perfect and works for every single point. Or it messes up so bad that it goes away from the data. If you have a linear regression model that goes too much in favor of the data, then we call it overfitting. And if it went too far away from the data, we call it underfitting. We don't want something to overfit. We don't want something to underfit. We want it to be optimal. In other words, we want it to be unbalanced. If you're overfitting, then you're being extremely biased towards the data. If you're underfitting, you're introducing too much variance in estimation. So it's called the bias variance trade-off. We know what the model is. What is beta 1 hat? The estimate that we had was linear correlation coefficient multiplied by the standard deviation of y divided by the standard deviation of x. This is also equal to Sxy divided by Sxx. Thus, denominator simply is the sum of squares for x and beta naught hat is y bar minus beta 1 hat x bar. Good so far. What is the property of an unbiased estimator? So we call an estimator to be unbiased if expectation of W is equal to W, but W is the estimator. Week 2023. Yes. What is the unbiased estimator for the average, the mean, the population? It's denoted by the letter mu. Yes. So you must have heard of the term sampling distribution. Yes. What is the difference between just the distribution of data and a sampling distribution? Bear with me, it is a bit theoretical, but you need this. So what is the mean of a sample? That's an easy question.
X bar.
Okay, how do we find X bar?
Sum of the values divided by the number of elements in the sample.
Okay. So I'm going to generate a sample. Now, do we know the truth in statistics? I mean, the true value? No.
That's why we're taking a sample.
That's why we're taking a sample. If we knew everything, why bother with statistics or anything for that matter? So give me a number.
45.
Another number.
E.
27.
A number that doesn't come from Dennis's mouth.
27.
27. And I'm going to generate a sample. I'll call it S. And for the sake of simplicity, you don't have to, again, know this. You're welcome to try this once I've released the script. Our norm, people who took contact. What is it?
R.
What does our norm stand?
It generates a normal distribution.
It generates a normal
Well, it
distribution.
doesn't generate a normal distribution, but you use it to look at the normal distribution essentially.
No.
Random norm distribution.
Getting closer. So you've got the generate part, you've got the random normal distribution part, but it's all jumbled.
Oh, it generates a set of values randomly from a given normal distribution.
Very good. It generates a random sample from a normal distribution at some value. So what I'm going to do is I'm going to generate a sample. Let's see, a sample size. $96. Just for fun. So 96, and this is the truth. I know the true population parameter, which is 27. With some standard deviation, I'm going to pick 2. 1 is better, but I'll just go with 2. Good. So what I'm doing is generating one sample. Do we agree that that data is from a normal distribution? Mean 27. Looks like it if you don't believe. always histogram. Looks like a bell curve. We can't expect it to be perfectly symmetric because this is a sample. Going to find the mean. The value of mean that I get from the statistic, will it be the same as the original parameter? No, no way. Would it be close to the original parameter?
More than
Should be, depending on the sample. Let's see. 26.93. Fascinating. Good. So I have one sample, I get 26.93. But in theory, whatever we have does not come from that one sample. There is more to this. Explain what that is. I am going to pick the estimator as the mean, sample mean. Suppose if you're not satisfied with one sample and say you want to collect a bunch of other samples, is it reasonable to have the exact sample size for every case? I mean, if we put a restriction, sure, but oftentimes different samples have different sample sizes. So I'm going to obviously set the sample size to be 96 for this case to keep things simple. Good. So what this means is I'm going to go for each, I'm going to collect individual samples. How many samples am I collecting? 100. What is the sample size for each sample? 96. And I'm computing the mean for each of them. Okay, so far. It has to be random again because this is statistics, which is why we're collecting different samples, even though the true parameter is 27. We do not know what that true value is, and things have to vary from sample to sample, and that is taken care of by the value 2. Yes, standard deviation. Now, 100 times, in other words, 100 different samples, each of size 96. And that's what I get. Yes. So take good look. Now, instead of just having 100 of them, let's say I have enough resources, I go for 1,000 different samples. I hire 1,000 different people. Each of them is going to collect and obtain a sample of size 100 from the population. So I'll go back to 100 ones so you can see. So that's the 100 one. And I have 64 breaks, which is a bit too much. Let's do 32 breaks. And that's the picture I'm getting. Is it perfectly normal? No. But where is the center? More or less.
Around 27.
Around 27. Going to increase the number of samples to 1,000.
Should have a standard deviation of 2 over the square root of 96 roughly.
What does it look like? Is it a bell curve? Yes. What is the mean? 27. Let's go for 10,000. What happened to that bell curve?
It became more or not.
Huh?
It looks more like a number.
It's getting better. So it's not going to break R yet. So we sort of attain perfection. What is the mean of that bell curve?
So
27. The variability, it seems like the 2 standard deviation, 3 standard deviation level is at 27.5, 26.5. I want to find the standard deviation.
2 over the square root of 96.
Should I find the standard deviation of the sample or the sample, this sampling distribution that you see up here? By sample, I mean S. By sampling distribution, I mean to say it would be S dot sum, which is all the sample statistics. I want to find the sampling distribution of the statistic mean, and I need its standard deviation. So SD, S dot sum, and you get 0.2038. And how do we get the 0.2038?
Take your original standard deviation and divide it by the square root of the number of elements in your sample.
You take the original standard deviation and you divide it by the number of observations in your sample. S over square root of n, sigma over square root of n happens to be 0.2021. If you go back to 2023, look at a textbook for 2023, you'll find that the sampling distribution for mu is normal with mean mu, but the standard deviation is no longer called standard deviation, rather it is called standard error. Sigma over square root of n. Another reason as to why we're trying to keep the same sample size, it's for theoretical reasons. That said, the average of the sampling distribution ends up being 27. 27 is nothing but the true mean. When our first started, I asked you, do we ever know the true parameter? You said no. What are we trying to imply here? If you sample time and time again, then the average of the sampling distribution of the estimator will result in the true value, which it did. Yes, the average of the distribution of the estimator sampling is the actual value 27.0. That average that we see, expectation, the average that we see for the sampling distribution is nothing but the expectation of y bar. That is the theoretical average of the estimator. The estimator under consideration is y bar. What does that statement say? The theoretical average, I even showed it to you using a simulation. The theoretical average of the estimator that we considered, which is the mean, will equal the true value. Yes? So I'm putting all these words because they all have names. So what we're trying to say is if you come up with a proper estimator for any scenario, doesn't matter, mean this is the easiest case, but all the statistics simply doesn't deal with estimating mean. There are other things. So what is the justification? If you find the expectation of the estimator that you have, it must equal to the actual value or the theoretical value. In theory, if it did, then you have an unbiased estimator. So the sample mean is an unbiased estimator for the population mean. Agreed with me? I'm going to make one slight change. So S dot sum is the unbiased one. Going to do biased. So if you multiply the mean by n, you get sum of observations. I'm dividing it by n minus 2. That is not the formula for the mean. But I'm going to say, well, that's another estimator. Let's say if this second estimator is a good choice. Original one, the biased estimator, both of them seem all right to me. But look at the mean. Original, biased, slightly up, yes. I'll do n minus 10. Original, biased, up 31. Yes, expected. If that is happening for really large sample sizes, let me pick something really, really large, and 27, 30.2. If the measured sample size is very small, let's say you have 16, forget about the sampling distribution. Even for a very small sample size, the mean gives you 27. Reasonable. The biased estimator does not. So you may say, well, 27, 30, not a big deal. Who cares? Well, science, it is important. 27 micrograms of fentanyl is different from 30 micrograms of fentanyl. One is going to kill you. Yes? So your estimation has to be important. Before I end, I'm going to ask a question and I'll show you next time. Based on all we did, started with unbiasedness of beta 1 hat and beta 0 hat. If you took the expectation of beta 1 hat using this formula, what should you get if it is unbiased? If the formula that we derived is unbiased, what should expectation of beta 1 hat equal to? The actual beta 1, not beta 1 hat, beta 1. The expectation of beta 0 hat must equal beta 0. If that happens, and that formula is an unbiased estimator, the other one is also an unbiased estimator. And it's going to be good. Place to stop. Questions, talk to me. If not, I'll see you next time.